Hello everyone. So today I'm going to present you a study entitled "A posteriori estimation of the performance level for a safety function using ISO 13849-1 standard." In this study, we took a design standard and we applied it to an existing safety function, so a safety function that has already been designed. So what is the issue that led us to this study? The thing is that in industry, there are many people who modify equipment or integrate equipment, and they are often asked to evaluate the safety level of circuits they have not necessarily designed. According to some people we met, they said how difficult such an exercise was. So we said it would be interesting to undertake a study which could be summarized in 3 questions. First, how to validate a circuit performing an existing safety function. 2, what is the feasibility of such validation procedure? And third, what are the difficulties and the limits of such procedure? So here are the preliminary steps. First, we must identify and specify the safety function we want to study in order to better know its features. Then we must choose the appropriate standard for the estimation procedure. And then we must know the required safety level. Why? Because the ultimate goal of this procedure is to verify if the existing safety level is greater than or equal to the required one. As you can see, for this study, we used an injection molding machine. This machine is located at the IRSST, and here is the name of our safety function. It's about stopping the closing movement of the movable platen when opening the operator gate, which is here in yellow. And to the left, we can see a diagram that represents the operator gate. And on this operator, there are 3 switches that are installed, and they indicate if the operator gate is open or not. So those switches are part of the electrical circuit performing the safety function. And during further analysis, we also noticed that the safety function is performed also by hydraulic energy. So for the choice of the standard, well, we had to choose between 2 different standards, the ISO 13849-1 and the IEC 62061. And since we had 2 types of energy, the appropriate standard for our case was the ISO 13849-1 because the IEC standard deals with electrical electronic components only, whereas the ISO standard is made for any type of energy, electrical and non-electrical. And here is the last step of the preliminary part of the validation procedure. As I said previously, we must know the required safety level. In our case, this safety level is called the performance level. So the required performance level can be estimated with the risk graph from the ISO standard, or we can find it in a Type C standard. In our case, we were lucky. We found it in a standard related to injection molding machine, which is the EN201. And it says for our safety function, the required performance level was the highest one, which means E. So those were the preliminary steps. Here are the subsequent ones. First, we must identify the designated architecture, which is the architecture that is related to a certain category. Then we must estimate the mean time to dangerous failures. Then the average diagnostic coverage. We need to verify the different measures applied to counter common cause failures. And we also need to verify the required for a safety-related software. But in our case, there were no safety-related software performing the safety functions, so it was not necessary. Then we had to verify the different measures applied against systematic failures. Then verify the ability to perform the safety function under foreseeable environmental conditions. And at last, verify if the existing performance level fulfilled the required one. So I will focus on the main assumptions. So those are the assumptions related to the first 3 points here. But before I will present you the results of the study, since the machine was used in the laboratory, we said, let's do the calculation for the machine working 2 hours a day during 5 days a year. And here is what we found. We found that, unfortunately, there were none of the 4 possible categories that was satisfied. But the minimum required score to counter the common cause failure was satisfied. We found a high mean time to dangerous failure, but a 0 average diagnostic coverage. And those results led us to this. Since the category was undetermined, there was an undetermined performance level. So we said, since we don't satisfy the required performance level here, let's see what will happen if we do the same exercise for an industrial context. After all, machines are made to work in plants. So we made the study for the machine working 20 hours a day during 350 days a year. It's for a plant in Quebec. Here's what we found. Category 3, we satisfied the minimum required score to counter common cause failures. There was a high MTTF and a medium average diagnostic coverage. And here's what we found. We found that the performance level was in compliance with the required one, which is E. So, as I said, there were many assumptions, but I'm going to give you only main examples. The first example was the assumptions made for the designated architecture. When determining the designated architecture, the big question was, what is the role of the components? And this was not easy, so we had to undertake a reverse engineering exercise with circuit analysis, and it's called failure modes and effects analysis. And thanks to those analysis, we found this 2-channel structure, which inputs are the 3 switches previously shown, and the information from those switches are treated by 2 safety relays. And the analysis helped us find that there was a 3rd safety relay that was there for a diagnostic purpose. And for the input, we found that, well, there were 2 hydraulic valves. And during the analysis of the circuit, we noticed programmable electronic card, which is here. But we had no information, unfortunately, from the designer, neither from the manufacturer, about the functions of this card. But we assumed that it was there for a diagnostic purpose. But since we had no information, we had to assume that the diagnostic coverage was 0. But in reality, if it wasn't 0, the results previously shown for the average diagnostic coverage would have changed. So you see, this is an example of the impact of the uncertainties in the hypothesis in the study. And this hypothesis introduces a limitation to the a posteriori estimation because without indications from the manufacturer or the designer, it is impossible to know the functions of the card that integrate a programmable component. And this observation also indicates that it may be easier to validate a circuit that has elementary electronic components. So here is another example of the assumptions made. This time it's for the calculation of the mean time to dangerous failure in the average diagnostic coverage. Here are the formulas that we took from the standard and then applied it to our case. As you can see, these formulas, they depend on the MTTFD formula for each component. And to determine the MTTFD for each component, we had to know the reliability data from the components. Unfortunately, those information were not available in the data sheet of the components. So we had to assume that the components were in compliance with the criteria in the standard, and then we could be able to use the information, the reliability data from the standard, and then apply it to our case. And the last assumption was about the mean number of annual operations, which depends on the conditions of use. And those two parameters, they affected the MTTFD and the DCavg, and sometimes the performance level. So as you can see, the curve on the top is describing the MTTFD, and the blue one is the DCavg, and there's a dotted line which marks it separates two zones, the one where we satisfy the performance level and the other one where we don't satisfy it. And this big difference could be explained by the fact that the conditions of use in the laboratory context were much lower than the industrial context. So maybe if we wanted to estimate the performance level for the laboratory context, maybe we should use another calculation method other than the one in the standard. For example, Markov's modeling. So if we take a quick recap of the questions previously asked, we will see that we have sufficient information to answer them now. So about the safety level of the circuit, we saw that we were able to estimate the performance level for the industrial context, and we found that it was in compliance with the required performance level, whereas in the laboratory context that was not the case. We learned that to estimate a posteriori a safety function, we must first identify and specify the safety function. Then, if applying a standard, we must choose the appropriate standard depending on the technology involved in our study, and then follow the steps suggested in the standard. And we realized with the assumptions that the a posteriori estimation is a difficult procedure to achieve due to the many assumptions made throughout the reverse engineering exercise, due to the lack of information that could be available if the designer was involved. And of course, this lack creates uncertainties in the results, which depend on the people who achieve the a posteriori estimation. All in all, carrying out an a posteriori estimation is possible, but the results should be carefully considered, because the accuracy of these results can only be optimized by surrounding oneself with experts in safety-related control system, or ideally by the designer. So this is the end. If you have questions.
Okay, thank you very much.